Welcome to The Explainer. Today, we're diving into the incredible journey of computing hardware, from these clunky, room-sized mechanical giants to the microscopic marvels that are, well, literally powering our world.
Take a look at this number, 5.3 trillion. Just let that sink in for a second. That is the staggering number of transistors we can now cram onto a single, massive, modern computer chip. It's just mind-boggling.
So, how on earth did we get here? How did we manage to build our entire future on something so ridiculously small? Well, the story isn't just about shrinking things down. It's a dramatic tale of brilliant solutions to problems that seemed completely impossible. Okay, let's get into it.
Our story really kicks off with a fundamental problem. How do you escape the sheer burden of doing all this heavy calculation by hand?
So way back in the late 1930s, you had pioneers like Konrad Zuse building these mechanical beasts like the Z3. For its time, it was a total marvel, right? It used 2600 buzzing, clicking electromechanical relays, basically tiny physical switches, to do its math. But man, it was huge, it had very limited memory, and it was super fragile. So fragile, in fact, that the original was completely destroyed in a bombing raid on Berlin.
And that was the real bottleneck, the physicality of it all. These relays, and what came next, vacuum tubes. They were big, they ran super hot, they ate up tons of power, and they just were not reliable. Progress was basically being held hostage by these clunky components. You couldn't just build a bigger, faster computer because you'd run out of space, power, and honestly, the patience to keep fixing the thing. What engineers needed was something totally new, a switch with absolutely no moving parts.
And this was the solution, the transistor. It was an absolute game changer. Look at this comparison. The old vacuum tube, big, fragile, a real power hog. The transistor, tiny, tough as nails, super efficient, and cheap to make. This wasn't just a small improvement. This was the spark that ignited the entire electronics revolution.
Okay, so here's the thing. While transistors solved one massive problem, they kind of created a new one. It's one thing to have a handful of these little guys, but what happens when you need millions of them? Or, billions? How do you wire all of that together without creating what they called the tyranny of wires? Just an impossible spaghetti mess.
The answer was the integrated circuit, or the IC as we all know it. Instead of painstakingly wiring every single component by hand, innovators like Robert Noyce figured out how to build the entire circuit, transistors, resistors, the whole shebang, on one single tiny slice of silicone. It was the ultimate act of miniaturization and integration.
And that one invention, the IC, it kicked off an incredible 50-year golden age, and it was all governed by a single powerful idea.
This observation, famously known as Moore's Law, basically became a self-fulfilling prophecy for the entire industry. For 5 decades, the path to more powerful computers was simple in concept, if not in execution. Just shrink everything. Every 2 years, you get twice the power for the same price. It was an unbelievable engine for progress.
And you can really see that exponential explosion right here. It's just wild. We went from small-scale integration in '64 with maybe 10 transistors to ultra-large-scale integration with over 1 million on a single chip just 2 decades later. That relentless, predictable pace is what eventually put a literal supercomputer in your pocket. But, a ride like that can't last forever. And it didn't. We finally reached a point where we simply can't shrink transistors much further without bumping up against the fundamental laws of physics.
As transistor scaling slows, we've slammed right into that physical wall. The industry has entered totally uncharted territory, and the old solution of just shrink it, well, it no longer works. That predictable biannual leap in performance that we all got used to is over.
So what's next? If we can't build smaller, we have to build smarter. And this has kicked off a completely new era of innovation, one that's focused on clever design and architecture.
The first key here is co-design. You see, for decades, the hardware folks did their thing and the software folks did theirs, in totally separate worlds. Now, they're being created in tandem, each shaping the other for maximum performance. It's a holistic approach, building a complete, optimized system from the silicon all the way up. Next up is advanced packaging. And the best way to think about this is like building microchip skyscrapers instead of sprawling single-story cities. By stacking chips in 3 dimensions, we can dramatically increase power and speed without needing a bigger physical footprint on the circuit board. We're building up, not just out.
And that leads us to chiplets. This is so cool. Instead of designing one giant, monolithic, do-everything chip, designers can create smaller, specialized chiplets and combine them just like Legos. This makes design way more flexible, much faster, and it opens up a whole new marketplace for innovation.
So this right here, this is the new formula for progress. It's a system where modularity with chiplets, 3D construction with advanced packaging, and holistic co-design all work together. And you know what's really wild? We're now even using AI to help manage the immense complexity of designing the next generation of these incredibly powerful systems.
This fundamental shift from simply shrinking to intelligently constructing, it opens up entirely new possibilities for what we can achieve with technology. The race isn't over, not by a long shot. It's just changed tracks. That's our look at the story of the chip. Thanks for joining The Explainer.